lecture 1B basics, and we will be doing some simple basics problem of thermodynamics using the book Fundamental of Thermodynamics by Bornack and Sontag, and we are using the 7th edition of that book. Problem number 2.39. A tank has got two rooms which is separated by a membrane. Room A has got 1 kg of air and volume of 0.5 cubic meter, while room B have got a volume of 0.75 cubic meter of the air with a density of 0.8 kg per cubic meter. The membrane is broken and the air come to a uniform state. Find the final density of the air. So this is just a simple problem of thermo, and which we are just finding the final density. So the final density would be the final mass of the which is in the room and the final volume of the room. To find the final mass of the room, final mass of the air in the room, so we have got the mass of the air and mass of the B. For the mass of the air in room A, it is given as 1 kg, while the mass of B is directly not given, but we have been given the volume and we have been given the density. So the volume multiplied by the density, that would be the mass. So we have got the 1.6 kg of total mass, which would be the mass of the air in the room when the membrane is broken. Now we have got the final volume of A and volume of B. Volume of A is 0.5 cubic meter and volume of B is 0.75 cubic meter. Adding them and we will have a final volume of room, which is 1.25 cubic meter. The density is mass per unit volume. So mass is 1.6 and volume is 1.25, and we have got the final density of the air in the room, which is 1.28 kg per cubic meter. Moving forward to another question. A piston and cylinder have a cross-section area of 0.1 square meter, has a piston mass of 100 kg resting on a stop. You can check in the figure. With the outside atmospheric pressure of 100 kPa, which is normal atmospheric pressure, what should be the water pressure to lift the piston? So we have got forces which would be acting from the top of the piston, and we would be having a force which would be acting from the bottom of the piston, or from the water on the piston. So once these forces are balanced, so in that case the water would be able to lift the piston. So whatever the force is acting on the top, if the water is able to get that force, in that case it will be able to lift the piston. So the forces which is acting from the top should be equal to the forces which is acting from the bottom. So forces which is acting from the top, so one of the forces is actually, we call it as the atmospheric force, which is equal to pressure atmospheric into the area of the piston, cross section area of the piston. So that means like that's the pressure force. Pressure is force per unit area, and so the force is pressure into area. So this is one of the forces which is acting on the piston. There's another force which is actually, we call it as the weight force. So that is m, mass of the piston, into the standard gravitation. So these are two different forces which is acting on the piston from the top. There would be actually a force which would be acting from the water from the bottom, and that is the pressure of the water into the area of the piston. So now that's quite a simple equation now. So if I just need to find out the pressure of the water, also the area is given. So my equation would look something like this. So that is my atmospheric pressure, MP, mass of the piston, G divided by the area. So solving that one, and we would be having a pressure which would be 198 kilopascal, and that pressure would be needed to lift the piston. from the bottom. Moving forward to another question. Now we have got a two piston and cylinder arrangement, and having two piston and cylinder. These piston and cylinder have got the gas chamber, and that is connected by a pipe somewhere here. The cross section area of A is 75 square centimeter, and cross section area of B is 25 square centimeter. I presume like that would be A, as it look bigger, and that would be B, as it is 25 cubic centimeter. With the piston mass of A, which is here, as mass of A is equal to 25 kg. Outside atmospheric pressure is definitely the normal pressure, which is 100 kPa, which is acting on both of the piston, and the standard gravitation, which is G. Find the mass of the B. So none of the piston has to rest on the bottom. So that mean like if mass of the B, let's say for example, is greater than its value, which we need to find out. If mass of the B is greater, then obviously this piston will move downward. When it's moving downward, in one condition it will be resting on the bottom. Then now if the mass of the B is less than what the value would be, so this piston will be actually moving upward, or this piston would be actually a little bit heavier, and this piston will actually move downward, and this would rest at the bottom. So the question is like, find the exact mass of B, so none of the piston has to rest on the stop. So again, first thing first, now the condition, obviously, sorry, the condition is, so we have to find out such a mass that none of the piston has to rest on the top. That also mean like we have to find the condition in which both of the pressure inside the cylinder A and cylinder B are equal. In that case, the mass of the in that case none of the piston would be resting on the stop. So mass, if the pressure inside this cylinder is equal to pressure inside this cylinder, so it will be definitely balanced, and there would be none of the piston would be resting on the stop. So finding out the pressure or the forces which is acting on the outside of the pressure of the cylinder A and from the bottom of the cylinder A, and finding out the forces which is acting from the top of the B and forces which is at the bottom of the B. Also for the cylinder A, we would be having mass of piston of A into standard gravitation plus the forces, pressure forces which is acting from the top, and the obviously the pressure which is getting pressure forces which is from the inside the cylinder. For the cylinder B, we would be having mass of piston in B, standard gravitation, pressure forces which is from there, pressure forces from which is from there into piston, and that one would be area of the piston B. Now I say like the condition was none of the piston resting on the top, and that on the bottom. That mean like the pressure inside both of the cylinder would remain constant. So if I'm saying like these two would be equal, them two would be equal, so arranging them, so that mean like P, that would be something like here is equal to mass of piston A into G plus P naught into A naught, sorry, A actually. So if I'm moving the area into, so dividing them with the area A over here, and if I divide this one, that will go on, that would be something like this. So more or less it will be something like this equation, and from B it will be this equation. As term is also equal, P naught equal to P naught, also just remove that one. And also if I just look at the standard gravitation, so that would be also gone, so that your equation would be something like this, and you can find the mass of the piston, which is 8.33 kg. Now moving forward to another question. A 5 kg piston in a cylinder with a diameter of 100 mm is loaded with a linear spring and the outside atmospheric pressure of 100 kPa as shown in this figure. The spring exerts no forces when the piston is at the bottom of the cylinder. But for the state shown, the inside pressure is 400 kPa with a volume of 0.4 liter. The wall is, so now for the first condition, the wall is now open. So let the air in. So now there's a wall in over here. So we have opened that wall, so we can actually let the air into the cylinder. Now the piston would be rising, and that piston is rising from for 2 centimeter. Find the new pressure when it rises towards the 2 centimeter, or which rise above 2 centimeter. The condition which is given is of the linear spring. So that means like the linear spring would be proportional to displacement, or linear displacement would be there. Now we have got the different condition. Now if I'll write the forces which would be acting on the top, so that would be one of the force which would be the force of the piston, which is mg. It will be one of the forces from the pressure and the area, which is P naught A, and one of the forces would be the spring force, which is normally Kx, and x is the displacement, K is the spring constant. So now if I'm adding them, so the forces which would be acting from the top would be equal to Kx plus P naught into area plus mg. This would be the acting from the top. From the bottom, definitely it will be the pressure of the air into the area of the piston. So these are the different forces which will be acting right now. But one of the condition which is given, that when the piston is at the bottom of the cylinder, there is no forces acting by the spring. So that means like when we are at the bottom of the cylinder, forces is only equal to mg and plus P naught into A, and that is what we call it as the forces which would be acting from the top. So now looking at this condition and looking at the equation of the linear, which is, if you remember from the previous classes, you people used to have y is equal to mx plus c. If I would say y was actually the y axis, m was the slope of the line, of the straight line, x was the x coordinate, and c was the y-intercept. So if I'm looking at this one, this definition, so my equation would be something like this. So in my term, it will be P pressure, which is actually at the y-axis. Slope would be equal to delta P by delta V something. X is V itself, and C is my y-intercept, which actually would be the P at zero volume. So that would be something like this one. So finding different condition from the equation. So for the P naught, again, if I'm writing the equation again, P2, that would be equal to slope, and that slope is, let's say for example, in here it's written B, and then obviously the volume over here V plus y-intercept, and that y-intercept over here is written A somewhere. So now what is actually y-intercept? Normally y-intercept is the condition in which the x-axis will cross the y-axis at 0. Or in other term, what we say, like, what would be the value of y when x-axis or the x we have got at 0 condition. So for the 0 condition, we have been given like the condition that the kx would be equal to 0 when we have got at the bottom of the cylinder. So at the bottom of the cylinder, we have got the equation, and that equation would be equation of the, let's say for example this one. So we would be having a pressure somewhere here, pressure into area of the piston, which would be equal to mg plus p naught into a. So this is the condition in which at the bottom of the cylinder, when kx is equal to 0, this would be the condition. This is the pressure we at the 0 volume, apparently 0 volume. So for that pressure, if I say, like, if I move this area into this one, and that would be something like this, I would need this pressure P over here. That is the pressure in which our x-axis was 0 when the volume was 0. This was the pressure. So once I find this pressure, I can find the slope of this line, and that slope of the line would be actually y2 minus y1 divided by x2 minus x1. So that would be the slope of them. So delta P divided by delta V, I'm saying. This would be the slope. Once I find this slope, once I find this y-intercept, I've got the volume at 2, V2 somewhere here. Just I put the volume V2. I did find out the volume V2 from this displacement, and obviously the actual initial volume was 0.4. So that volume plus the displacement volume, we would be actually find out the volume V2. Once we find volume V2, we can find the pressure P2 over here. So this is the whole method of doing it. If you find another method easy, yes, you can find the question, or you can solve the question using that method. I hope you understand this question, and I hope you understand these questions. If you have got any question related to these lectures, you can post it on the classroom, and I would be able to answer that one. Thank you very much. Have a nice time.